Yes, you can.
Yes. Okay, great.
So yeah, let me introduce again Dr. Leonardo Sandonas. He's a research associate at the Technical University of Dresden. Previously, he was a postdoctoral researcher in a group in the Theoretical and Chemical Physics from the University of Luxembourg. His research focuses mostly on machine learning and its application to different fields of computational chemistry related to biology, medicine, and pharmaceutical fields. Well, he has received some awards in this regard, including some of the Royal Society of Chemistry. So, the floor is yours.
Thank you. Thank you, Miguel, for the introduction. So, thanks everyone for being here. So, since I was invited to talk about applications of machine learning potentials, so I tried to cover some of the projects that we are working in TU Dresden. But before talking about machine learning potentials, so I want to talk about how to make more sustainable machine learning. Because everyone has been talking about okay, let's generate big data sets, also train big models and so on. But no one is talking about how much damage we are making to the environment, producing these data sets, also training these models. Now we have big models, not like a machine learning potential, but like a large language model, which produce more damage to the world. And well, we are suffering that, right? So it's more work, and then we are now suffocating sometimes. Our idea, or well, the discussion that we had last year in this conference that we organized in Dresden about sustainable machine learning, was to find a way or to discuss how to make machine learning more sustainable from the computational point of view. Currently, what we are always discussing is how to generate data sets, representations, how to improve the efficiency, accuracy, scalability, and transferability of machine learning models. But we are now still discussing how to integrate this with big pipelines that you can really produce some experiments and try to optimize everything, for instance, with self-driven labs. So we are still not there, and I think we have to go in that direction because, if we continue optimizing this, we will never know if our models are already ready for some discovery materials or drug discovery. So this is a discussion that we did. We had in the last conference, and we brought a perspective. You can find it here. And now we are also trying to collect some data, to tell the community how much CO2 you are producing every time you generate a data set or every time you train a machine learning model. Just an example here. For instance, this is to predict the CO2 working capacity in metal-organic frameworks. If you go from a simple model of GCN or SNET models, and then you have here a transformer, which is of course more accurate, you see the mean absolute error reduced, but also you can see the number of parameters also increased. And of course, this will have a consequence. Then you can see by an increase or by a decrease of 28% in the mean absolute error, you have a 3 orders of magnitude more in the emission of CO2. So this is what you care or not. This is something I think the new generation has to think about. How to make things more efficient in order to reduce the emission of CO2. And just to give some numbers that we are collecting, so it's still unpublished data because we are continuing collecting this. So here you can find the famous data set, for instance, materials project or more that everyone is using. So again, the GEMS data set like Adil was talking about. So they are emitting really tons of CO2. Or no, sorry, they are not emitting. They already did. So we are suffering all the consequences. So then, how to make this generation of data set more efficient? So that's why I think it's the direction the machine learning has to go, because otherwise we will continue discussing how to generate more data, then at the end we generate tons of data sets, but then also we contaminate the environment, and then the air will be more warmer and so on. I don't say that it's wrong what we are doing, but let's try to make it more efficient. And here you can see also how much CO2 we emit just by training these machine learning models. This is the information that we got from papers. If the authors of the papers are here, maybe you can correct me. So there are some tools you can convert how many CPU hours you spend and how it's correlated with the CO2 emission and also how much power you spend. So this is what we did in this paper, in the perspective. And then we are trying to collect more information in this regard. No? If you have some data, like how many CPU hours you spend your data set generation, so just send it to us, and then we can also publish it in this paper here. No? It is just to tell you, like, be careful with what you are doing. So just pay attention to this, because I mean, maybe for now, for us, we are not suffering the same consequence, but in 10 years, 20 years, it will be more consequence about it. No? And okay, so now this is just to warning you about this problem, but now we will start with what we came to this conference, which is about machine learning potentials. And then I split my presentation in 3 parts. So the first one is to talk about like how to generate machine learning models for materials science, especially for investigating defective code. The second part is to talk about machine learning potential for biomolecular simulations like functionalized nanoparticles, RNA, and one method that we developed last year, so AKTV. And the last part is how to use these methods in order to make the generation of data set more efficient. So I call this a new framework CALPA, which is quantum-aware learning for property-space augmentation, because now we're using generative AI combined with machine learning potentials just to optimize the generation of data sets. Because as I told you before, so you just generate data sets like brute force, let's say, you can generate tons of CO2, right? And this is what at least I will try to avoid. So, okay, then let's start with the part number 1, so which is the machine learning potential for COF. If you are not familiar with this covalent organic framework, so they are 2-dimensional materials. They can be generated by combining 2 main building blocks, which is the linker and the core. And then you can have like a chemistry, so you can have many different building blocks, and then you can have tons of covalent organic frameworks, right? But from the experimental point of view, these materials, most of the cases, they come with defects. So you have some holes, so like a pore size, as you can see here, or also you can have grain boundaries. And how well can we use machine learning potential to study these systems? I mean, most of the, as we saw in the previous presentation, so we are using like machine learning potential for biomolecules, but there is a limit, right? So, I mean, you cannot go like 10,000, 20,000, 40,000, and then the number of nanoseconds that you are simulating is reduced. And if you want to study these materials, I mean, with effects, you at least need one system of 40,000 or 50,000 atoms, because otherwise it won't be representative that effect that you are studying. Then what we did was to consider one data set that was already published, that it contains only 36,000 conformations of 23 strain COF. And this data set only contains covalent organic frameworks with 3 different compositions, but in different combinations, no? So different building blocks and also strain systems and equilibrium systems. Then, since we want efficient model that is able to, or we are able to run very long simulations and also like with a large number of atoms, then we did this benchmark here. And also we benchmarked the foundational models that Gabor and Ilias were discussing yesterday. This makes of 24, MP0. And also we fine-tuned this model using a simple multi-head replay fine-tuning. And we saw like the accuracy in this data set, improve using the fine-tuning. But the number of atoms that you can run in the simulation it still remains quite low, for instance, around 20,000. But if we start developing a model from scratch and only modifying the architecture, like for instance, 48 channels, only one interaction layer, and then a cutoff of 4 angstroms, then we found like we can increase the number of atoms in the simulation and still keep good accuracy in the data set. So then at the end, from this analysis, we found like this was our best model, which can be used to study systems of 140,000 atoms. what we really need for our simulations, especially for large-scale defective systems. I mean, and then we call it QCOF because quantum COF, so very original. So and then we use the model to study how the mechanical properties of this defective COF will be affected under strain. So then we start stretching the system. And if you are not familiar with material science, so something important for a material to be useful is to know the Jones modulus. And to know the Jones modulus, so you need to know where the material will break, the breaking point of the material. Then what we did is, these are pristine systems, and then we only strain the system in the X direction or zigzag direction and the unchaired direction. But then by introducing defects, we saw this breaking point also reduced. Then there is an influence of the defects in the Jones modulus, and this is what we found here. But we were able to study this only using the QCOF, because if we use the typical React FF classical force field, then it was not possible to study this. No? And then we say, okay, so in material science, it's quite important to understand the mechanical stability of the system, but also something important is to understand our observables, like thermal properties, for instance, thermal conductivity. And thanks to the implementation that the MES people did, the interface with lamps, so we were able to run simulations like non-equilibrium molecular dynamics. And if you are not familiar with this, so you have to impose two different thermostats, one the hot region and one the cold region, and then you generate a temperature profile. And based on this temperature profile, so you can compute the thermal conductivity by computing the gradient of the heat flux. Then we did a calculation for all the systems that we studied, pristine and defective. So and then we found this. Then you can see for instance, in this case, the CTF1 has a larger thermal conductivity than this one, than the other one, the U1, because it's expected, because also it's more compact COF, so it's not so poor like the other one. But also we saw the defects. If we introduce defects in this one, the second one, then the thermal conductivity was not affected at all. So, maybe the amount of defects we introduced was not enough to reduce the thermal conductivity, because that's quite expected. When you introduce defects to a system, then you will reduce the thermal conductivity because of the scattering. But here we didn't find it. But in your case, since it's a more compact cobalt organic framework, then you could find this. So, but then this was very interesting findings, and no one has done it so far with machine learning potential for COF, and we were the first one. That's good. And if you want to read more about the preprint and the discussion that we did, so you can look here. Now this paper is under revision, but I think the feedback was very positive. So. Okay, this is one work that we did in material science, but now maybe more people are more interested in the biomolecular simulations. Then here we have done different things. And also recently I summarized some advancements in this community together with Adolfo. We wrote a mini review about how the community of biomolecular simulations is moving from the machine learning potential side and also from the coarse grain side. And we did a summary here for the atomistic machine learning models, which is maybe already now outdated because it was 24, 25, but now in the last year there has been new models. So here, we split all the models that we could find in 4 different groups: models generated with equivalent neural networks, with hybrid machine learning, molecular mechanics machine learning, so then machine learning augmented semi-empirical methods, and kernel methods. And so far, one of the top, let's say, in the number of atoms was Allegro and Grappa, no? So they were able now to, you can use them to study systems with 1 million of atoms. I'm not familiar with the implementation, but if you want to know more, so you can visit our review, you can read it. And also Solar, at that time was here, but based on what Adil was saying, maybe Solar is already moving up in this plot. And MES potentials also were here. But I mean, this was, as I say, like 1 year ago, 2 years ago. No? So in our case, our model that we generate with semi-empirical methods is still here, but I mean, we're trying to also move it up this method. No? So I mean, you can read the review. I think if you are new in the field, it will be a very nice review for you because summarize all, I mean, all of these methods, like a very short, I mean, the main features of the method. No? Then in this presentation, I will focus mainly on the equivariant neural networks. And one of the first applications that we did together with Roberto, so it was a student from Italy, was visiting our group, and he was very interested to study how we can functionalize gold nanoparticles for biomedical applications. I mean, there are many biomedical applications for this kind of systems, but one that we were more interested in was the interaction of these functionalized nanoparticles with these microglobulin filtration effects. So they can, I mean, so far we are not still there. What we say is like, okay, first let's try to understand if the machine learning potentials are good for interaction between molecules and the gold nanoparticle. Because if the machine learning potential is not good for the functionalized gold nanoparticle, then we shouldn't go to this kind of interaction, right? So then this is what we did. So we took this data set, it was already published, of gold nanoparticles functionalized with some methyl groups or thiolate protected groups, but also we modified the linkers now. And then what we did was fine-tuning of the model. So thanks to the presentation from yesterday, I don't have to explain this fine-tuning problem now. But we select only 600 conformations from this data set, and we run single pore calculations at the same level of the OMOL data set because we want to use the OMOL thread in the maze models. So and then we select, okay, let's select this 600 and then run single pore at this level. No? And now you will see the results. So, I mean, these results are in agreement with what Gabor presented yesterday, because if you see, like we use the baseline model, the MH1, then it cannot predict correctly our data set, but the OMOL yes. But then if we do the naive fine-tuning, then it can predict correctly our data set, but the OMOL, it lost complete information about the OMOL data set. And then we try also multi-head, LoRa, and wave freezing, and then you can see here the performance. And at the end, our best model for us was the LoRa. So, I mean, here we have very good accuracy in our data set, and I think we have a decent accuracy in the OMOL data set. We don't go for the wave freezing because, I mean, here already you can see the difference. So, and also like we did some validations, I mean, core validations that will not show here because we are still working on the paper. So maybe it will come out in 2 weeks or in 3 weeks, the preprint. So I just pushing Roberto to write it fast. But then, I mean, here you can see already the effect of the fine-tuning method that you are using, I mean, to improve even this small system, no? Because it's not a large system. I mean, it's just one gold nanoparticle with 20 or 30 molecules functionalized there. But then we say, okay, then let's try to see what else we can do with this fine-tuned model. And then we're also comparing the vibrational spectrum for a small nanocluster. And here you can see the performance. I mean, some of them overlap with the DFT reference, which is in black. But to quantify this, what we did was, I mean, to define a parameter, which is the error in the geometry and also the error in the spectrum. And then we found at the end, like the LoRa model was the best here. You can, I mean, this was the Pareto front, let's say. And then we just tried this model for something more interesting, like for this biomedical community, which is the coalescence of 2 nanoparticles. And then you can see this is the starting point and this is the final point, but only after 10 nanoseconds. I mean, for these kind of simulations, you have to run it like a more than like a 50 or maybe 100 nanoseconds because they need to see really if this coalescence effect is quite stable or not. So But I mean, we're continuing running now, so I mean, I guess for the publication will be complete, hopefully. But yeah, this is what we are doing with this fine-tuned model, and which is working for now is working good. And then, of course, the next step now is now the interaction with the protein, and we see what will happen there. So that's one of the applications that we were doing recently. But the other one is to, we also want to enter in the field of RNA modeling. But I mean, we are not too ambitious yet. So we don't want to go to this big system. So we are starting with a simple adenine dimer, which is already very problematic, to be honest. So, I mean, this adenine dimer, so it's very flexible, even in water. I mean, so on gas phase, I mean, so it brought many troubles to us. So what we did was to generate a data set, not just like a simple MD simulation at 300 Kelvin. We use enhanced sampling methods like a vertical chain to generate a very comprehensive data set that contains all the structural characterization for this specific dimer. No? And then once we did, we generate a data set from classical force fields, then we run single point calculation using quantum mechanics. And in this case, I was very curious to see like how time banding and DFT they can compare producing the data set. Because I mean, there are many discussions to understand which level of theory is the correct for generating data sets. And then I say, okay, let's try a simple time banding model like a DFTB. So, and then the DFT level was PV0 MBD, which is, I mean, as you already heard, it was the best model like for solar or the best level of theory. Then this was a characterization that we did from the classical trajectory. We determined 6 different clusters in this RNA dimer. I mean, it means like our machine learning potential should be able to visit these 6 different clusters. If you don't find these 6 clusters in the machine learning potential, then something is wrong with the potential. So then what we did was, okay, let's analyze like how is the energetics for the DFT and the DFTB, and we saw some difference in the distribution of the total or atomization energy, but also in the van der Waals energy. No? So if you use the van der Waals energy computed with DFTB and DFT, of course you will get different representation of different distributions, which is quite critical, no? Because now it tells you like depending on the level of theory, also the van der Waals correction will be different. So then that's a problem that I don't want to discuss now, but I mean, it's an open question still. And then we also analyze fluctuation of the charge. I mean, we have all the trajectory here, and then we see like how much the atomic charge fluctuates in each atoms. And we saw that here's the standard deviation, and it's quite high, no? Especially for the atoms in the phosphate group. So this is quite interesting, but this is everything what the machine learning force field should be able to analyze or understand as well. So now let's see what happens. So here I present the Pareto for this the y-axis. You see the concentration of the A4 cluster, which is the this one here. This is the A4, and the A4 is the cluster, like in many experiments, they will discuss this structure. So many experiments, they don't determine this one, but they will find this one. This is the most stable conformation. So that's why we analyzed that one mainly in this paper, but then also we analyzed the stacking fraction. So then from the train method, which is the replica chain method, so we have this reference. And then we, all these methods that we develop with the data sets, we use only maze. So we use the maze architecture to train the machine learning force fields with the DFT and the time banding data. And also we compare with results obtained by maze polar and solar. We have to use maze polar and solar because they are the only models that allow us to introduce some charge during the validation. No? The other models, they are mainly for neutral systems. And then we run like 3 different trajectories of 10 nanoseconds with all the models, and these are the results. No? And as you can see already, like mace polar and solar, they have a preference for the A form, which is quite far from the reference from the classical trajectory. But in the case of our models, since they were trained on the classical trajectory, then they are closer also to the reference data. But in terms of stacking fraction, so our models fails. But I mean, solar and mace polar, they have a stacking fraction because it's correlated to the A form preference. I mean, how we know this? We also did the cluster analysis. And then here already, you can see like there for solar and mace polar, there are some preference for the A form, which is in orange. And in the case of the time bandy and the DFT methods, there is a preference for the unstack. But what does it mean that? So why time bandy and DFT, they prefer to be unstacked? So in other words, this will mean that there are more transitions between the clusters. So some machine learning force fields prefer to travel from cluster to cluster than remain in one single cluster as solar or mace polar. So which is good. I mean, because when you have like a structural transitions, then you have to visit different states, and that's why people use the replicate chain. So like then it seems like our models are learning the replicate chain trajectory, but it's not sufficient. So something is happening, like they are not able to equilibrate the visit over all the clusters, because this is the reference for the replicate chain method, and then this is our results. So we have good results, but they are not the best. But it's very promising in this direction. And what we are proposing in this work is like now machine learning potentials for biomolecules, they should be also validated in this way, not just energies and forces. So you also have to understand like how transitions happen in biomolecules, because this is more relevant for the biophysics community than the energies and forces, because I mean, everyone can predict energies and forces by now. So then this is something like we propose in this paper, and then for now it's well received by the reviewers, but let's see. So good. So then now coming back to this plot, so I will present one of the methodologies that we developed also recently, which is the machine learning augmented some empirical methods. This one I started when I was in Luxembourg with Mirela and Alex, so like 3 years ago. And then, well, if you are not familiar with some empirical methods, one of them is density functional time bandy. And this method has been used for different applications like molecular self-assembly, biomolecules in water, molecular crystals, and molecular transport. And the beauty of this method is like you can split the energy in different components. Because now you can consider this one, the electronic energy, as one function, let's say. So one component that you will not modify, but then you just focus on the repulsive potential, which is always the problem in the FTV. Because the FTV has an issue with the repulsive potential because many people parameterize it with like a pairwise interactions, which in reality it is not. So then the repulsive potential has issues with accuracy and general validity. That's why we decided to remove it from the DFTV part, and then we replace it with a many body machine learning potential. That's I will show you here. So what we did was to use the electronic components from the DFTV formalism, but the repulsive potential now is replaced by a many-body delta TV potential. And this many-body potential will be trained, or it could be trained in the QN7X dataset or the D-Shaw dataset of molecular dynamics. So we benchmark like how to produce the best many-body delta TV potential, and what also using 3 different architectures, SpookyNet, Allegro, and Maze, and these were the results. Here I'm comparing the mean absolute error in the prediction of interaction energy and in the prediction of atomic forces for this dataset of molecular dynamics. I guess we are familiar with the X66 dataset. And then what we saw is like the spookiness models, they were quite far from the reference. Also, this model here was our previous model, which we published like 5 or 6 years ago. And then if we use MACE, then we have two models here, MC1 and MC1 and MC2, which means one means like it was trained only Q7X, and two means like it was trained in these two datasets, the combined datasets. And as you can see, the accuracy in forces is quite similar, but the accuracy in interaction energy is much better for MC1, which is kind of unexpected, right? Because here you don't have information about molecular dimers, but you still can predict molecular or interaction energy quite good. So this is what, I mean, that was the reason why we decided to select MC1 for further validations. And then, well, we ran MD simulations for more complex molecules like saprinase and the ligand 2Q5K, and also we compared to XTB and the standard DFTB, and also a reference machine learning potential. And in all of them, our model, it was performing much better than the other ones, you know, in the prediction of atomic forces. And then also we compute the vibrational modes for the amino acids, and also our model, as you can see here in red, in green, so it was performing better than the other models, no? In predicting vibrational modes, the maximum frequency, and the comparison with the reference geometry. So then we managed to improve the DFTB methods, and now we have accuracy close to PV0 and VD for these molecules. But in this version of the model, we were able to study only carbon, nitrogen, oxygen, and hydrogen-based molecules. No? Then, together with another student, Sekim, now we use QSML, and we expand the chemical space of our models, and now we can study phosphorus, sulfur, sodium, and chlorine. So now we analyze, for instance, in the new model, which we call it EQDTV26 because well, it was developed this year. So then we analyze the performance over the complex chemical space in QSML, because QSML has molecules which contains even up to 7 different elements. So it's very complex data set, but very interesting, and it's helping a lot to develop this model. So then what we did is similar to the previous model. So we compared the performance with the AKTV25, so which is the model from last year. And then we reduced now the performance in the S66, we reduced the error in the S66 data set. Also, we reduced the error in flexible molecules. And also, we have much better prediction than the FTV3 in the quick data set, which I really was showing before. So these complex molecular dimers. So then really our new model is much better than the previous model. So and then we can use it for other applications now. And this is what I will present next. So now I will tell you like how we are inserting these machine learning potentials to augment the property space of certain data sets. So, I mean, this work I started with Michael, a student in TU Dresden, and also Julian, a researcher from Pfizer. So our idea is the following. So we have an initial data set, but we don't analyze the conformational space. We analyze the property space, because we think like it makes more sense to analyze the property space, especially if you are targeting against certain properties, not like a homo-lumo gap or a stability dipole moment. So why to go to the conformational space if at the end you want certain properties? So this is our idea behind this. And then what we are doing is we implement this AKD, where Julian did implementation of the diffusion model here, and we are using diffusion model now to navigate the property space here. And what we define is a trajectory in the property space. So we decide from where the diffusion model will go in the property space. For instance, you define the initial point and also the final one. No? And then you build this loop. So you define so you train the model, let's say like for 50 epochs, in the first point, then you generate molecules, then you optimize the molecule with the AKDTV model that I presented before, because we want very good or accurate geometries. And then you can compute the properties either with FHIMs, if you want the FT properties, or with the F3 plus, if you want time bandit properties. Then you do like a filtering criteria, or we define this screening criteria like for property accuracy and also the SA score, because we want molecules that they are possible to synthesize. And then we start augmenting the data set. And you can repeat this loop until you want, so until you explore the property space that you want, and especially if you are focusing in certain region of the property space. And then at the end, you have a final data set, which is the initial data set plus the new molecules that you generated. So I think in this way, you can more efficiently generate a data set because you just focus on the regions like you are really interested. So you don't have to explore everything, all the conformational space. You just have to focus on the part that you are really interested in working on. So, for instance, why generating molecules with 10 EVs of homolumo gap? I mean, no one cares for application of that, no? Or dipole moments of 20 device or something like that. So we want molecules like they are interesting for certain applications. So, and this is the framework I call CALPA, for the quantum aware learning property space augmentation. And so it will be also published soon in the next few weeks. But then we say okay, but first let's analyze how these diffusion models scale, because if we want to go to large systems, then the scaling should be good. Then what we did was to use two data sets, like everyone knows by now, I guess, like Q7X and the Aquamarine dataset. The Aquamarine dataset covers all this space, and the Q7X is on here. And but you will see in a moment, like if your dataset doesn't contain built-in blocks, like you have in the Q7X dataset, then your diffusion model will not be able to scale properly. So you only don't need a large molecules in the training, you also need a small built-in blocks. For instance, you do a training only the Q7X dataset, this is the relative error for molecular polarizability, you increase the size, and then you're already, after molecules with 24 atoms, you're already far from the, from the 0 point here. In the case of Aquamarine, if you train a diffusion model only with Aquamarine, then you have problems in the low scale, so in the small molecules range and also in the large ones, to predict the properties. But if you combine two, large with a small, then you correct the low range of sizes or the low part here, and also the high ones. And then Aquamarine has only molecules up to 92 atoms. In this case, we were able to generate molecules up to 102, I think 110 atoms. So then the scaling of this model was improved by combining one data set with small built-in blocks and also large molecules. And why we need this? So, one application that we're presenting in this work is to study allosteric graphs. Because data sets for this kind of studies, they're very reduced. So you will find only maybe 200, 300 molecules max. So you will not have more than that. Especially you want to focus on molecules like they're in the phase 1, phase 2, phase 3, or they're already in the market, right? So then what we did was to focus in a special data set of allosteric graphs. We have only 238 molecules. And then we generate conformers using XTV, but we optimize everything with AKDTV, because now we managed to optimize our AKDTV model, and we can use this one in this framework. Right? Then we generate around 6,000 conformers, but based on the previous experience with the Aquamarine dataset, we combine this dataset with the Q7X, and now we have the QMX dataset, allo QMX dataset. And this will be the starting point for the CALPA framework. So you can see here you can see clearly two blocks, right? So this part here corresponds to the QN7X, and this part here corresponds to this 6,000 molecules or conforms here. So then what we did was to navigate for regions like you don't have so much information or you don't have any conformer or any allosteric block because we want to generate new allosteric blocks. So I mean, we don't want to explore regions like they already exist on molecules there. Of course, I mean, we have to start from points like, I mean, once you try the method, you will see like you have to start the training from regions like they are a bit populated, but then after a certain point, so you can go to very sparse regions of the property space. And this is just about proof of concept, but I mean, you can apply this methodology for any kind of study that you want to do. No? So, and then we found molecules in this sparse region of the property space, like only 4 molecules, but I mean, we just need 1 to work, right? So we don't need 4. I mean, if 1 works, I think it's good. So then we analyze the new conformations. So we generate 129 new molecules. And we analyzed the chemical diversity and the structural analysis, and we saw like the new molecules in red, they have the same chemical diversity as the original data set. I mean, there are some difference, small difference, but they still have the same elements, except phosphorus, because we don't have so many molecules based on phosphorus in the original data set. There's only 1 or 2, maybe. So. Then, I mean, in terms of geometries, so we expand the angles in the previous data, in the initial data set. So here you can see, so we are covering regions like they were not populated before, and which is good, no? So we are creating new molecules now. I mean, this is unpublished results, but I mean, it will come soon, and then you can use also the methodology. So, I mean, the idea is not to stay here, so we will try to validate the methodology with more interesting applications, and you will see in the future. So then to conclude, so this is what I want to present today. So these 3 different studies that we are doing in this group in Dresden. So we are working in material science, biomolecular simulations, and now we are implementing these methods in the CALPA framework, and now you can navigate the property space of any kind of data set that you want. No? So with this, I would like to thank everyone involved in this study, and also the funding, the computational resources. And if you want to receive the updates about these studies, so then just go to my website, which is not late, but I mean, I will do it maybe this week. So I think like the main papers are already there. So and then, well, thank you everyone for the attention.
Thanks a lot for this really nice talk. We have some questions in the chat, and we have like 5 minutes for additional questions.
I don't know if so thank you for the talk. I have a question about your ML simulations. So you showed that like solar and mist for 1 is not super accurate in MZs. But did you check like just like test errors on some subset before doing simulation, whether it's reasonable at all to do those? Maybe it's like super out of training set.
No, the errors for solar they are okay. For mist, of course, not, because it's different level of theory. So, but for solar, they're still okay because we have BB0 and BD, so and then the errors are not so high.
So what is
it's 0.8 and forces.
0.8 kick-up or more?
Answers, yes. Which is, I think, for some structures that you've never seen, like, because remember, like we have charge systems, so they are negative charge because I mean we are not considering the ion here. So I think it's quite reasonable for this.
Yeah. This is related to one of the questions in the chat. Edward Mendez is asking, RNA is highly negatively charged biomolecule, and a solution is often encountered with magnesium 2 ions.
Yes.
How do you take this into account, the effect of these divalent cations in your model?
The trend simulation contains ions, so these simulations contain the ions, but in the machine learning potential, we are training on charge systems. So like we consider the system minus one charge and then that's it. So, but I mean, we from the classical four fields we compare like with let's say like the experimental value ionic concentration and without ions, and the population. So I mean, of this cluster didn't change. So it seems like this population is not affected by the ion concentration, which is the main argument for us to train the machine learning four fields.
Okay. Otherwise, I have a question myself. When you saw, I think it was slide 28, when you saw like the property space. Yes, at the very end.
This?
Yeah, this one. How important, because you mentioned that it's really important to cover the property space of the target properties you want to achieve, but how important is it to have like a continuous representation of your property? Like, does having gaps between different, like you can clearly see that you have clusters of properties, does this affect a lot the generation process, or is not that relevant?
The most important here is not these gaps, is to have information of the building blocks.
Okay.
Because at least with diffusion models. So maybe with another generative model, so it will be different, but when they generate a distribution of distances and we learning the noise, so then if you don't have information of this distribution, then it's a problem. Because I mean, you need like somehow to control the short range information and the long range information. So that's why you have information, the building blocks helps a lot.
So, well, thanks a lot. Thanks, speaker again.